morning, guys. Welcome to the class of CE331, Environmental Engineering 1. So, today we will start from the aquifer. So, first of all, what is aquifer? Aquifer is basically the water bearing soil layer. That's it. Okay. So, for example, this is your ground surface, and if we have groundwater available, it at this level, groundwater, how does it remain in the soil? Basically, you have the soil particle, right? You have the soil particle, and in between the soil particle, you have the pore, right? This pore, am I right?
Yes, sir.
Okay. So the water actually remains in these pore spaces. In these pore spaces. Okay. So this is actually groundwater. Call it groundwater. And this layer of soil which contains the groundwater is called the aquifer. Aquifer. Okay. So water table. This is the ground surface here. This is the ground surface here. Okay. There is undulation. You can see there is undulation. This is the ground surface. Okay. Yeah, this is the ground surface. Now, where is the water table? The water table is here. Okay. The water table is here. Now, you can see there are two types of ground aquifer. One is unconfined aquifer, another one is confined aquifer. So, what is the difference between these two? First of all, look at the confined aquifer. Are you following me, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Look at the confined aquifer. Where is the confined? This one is the confined aquifer. This portion. Take this one. I mean this portion. What is happening here? You can see that in this soil layer, around the soil layer, bottom, there is a confining impervious stratum. That means this is a rock, solid rock, and from which the water cannot pass. So this is a solid layer. So this confined aquifer is confined at the bottom with a solid rock layer. Furthermore, this aquifer is also confined at the top by a confined impervious stratum here. That means this aquifer, this one, is confined by rock, impervious rock, both at the top and at the bottom. So this is called confined aquifer. Is it clear?
Yes, sir.
Yes, sir.
Therefore, the flow in this aquifer, in this confined aquifer, is kind of a pipe flow, and water is flowing from there. So this is kind of pipe flow. Water is flowing, as you can see, the direction of the arrow flow is in this direction through a pipe. But in case of unconfined aquifer, if you see here, this layer, that at the bottom there is an impervious stratum, that's okay, but at the top there is no confining impervious stratum. Yes, there is soil particle, there is soil particle, There is soil particle, that's fine, but this is not an impervious stratum. That means this is not a solid rock. That means this is not confined. This is not confined. So this is unconfined aquifer. Clear?
Yes, sir.
Yes, sir.
Okay. Now the thing is, in unconfined aquifer, this is kind of open channel flow, and confined aquifer is kind of pipe flow, and this is kind of open channel flow. So in confined aquifer, since this is like a pipe flow, the water is under pressure here. The water is under pressure here. Therefore, if you um, inject, if you inject tube well here, it's like a piezometer, right? Like a piezometer in a pipe. If you inject this through the pressure, water will flow. Through the pressure, water will flow. Okay,
Yes,
clear.
sir.
Sometimes maybe above the ground. Maybe, as you can see, the ground level is here. The ground level is here. Okay, the red color actually. The piezometric surface. Where is the piezometric surface? Here is the piezometric surface. This line. This line is the piezometric surface. That means if you inject a tube well here, the water will rise up to this level. Up to this level. Up to this level. So in this soil, if a people is standing here and the people is standing here, here you will see that after injecting the tube well, automatically the water is flowing out, right?
Yes, sir.
Yes,
So this
sir.
is
Yes.
flowing artisan well. Here the soil surface is at this level, but the piezometric surface is there. So these people will see that this person will see that water is not going above the ground surface. Unlike to this case, here you will see that the water is below the ground surface. So this is non-flowing artisan well. Okay. Now, if the tube well is in the unconfined aquifer, as you can see, this is at the unconfined aquifer. This is at the unconfined aquifer. Previously, it was the previous two tube wells were in the confined aquifer. Now, in the unconfined aquifer, here, um, the water table, there's a mistake here basically. The water table will not be clear here. Okay, up to this. Now, here, the water table there, will be there, because in a channel, open channel, if you put a piezometer here, where the water level will rise at the same level, am I right?
Yes, sir.
So this is the water table, water level for the unconfined aquifer. So the water level will be here. So water table wells, these are the water table wells. Water is not under the pressure, therefore the level will be same level. Is it clear?
Yes, sir.
স্যার এটা স্যার এটা কি বললেন স্যার যে কি না থাকলে এক এক লাইনে থাকবে?
Okay. Basically, the unconfined aquifer is kind of open channel flow. In an open channel flow, what happens? If you put a piezometer here, the water level is the same. Water level in the piezometer, water level in the piezometer is same as the water level in the water surface. Am I right? Same level. Am I right?
ইয়েস স্যার।
Exactly the same thing is happening here. Since these two tube wells, this one and this one, are in the unconfined aquifer, so the water level in these tube wells will be at the level of the ground water level. That means this and this level will be similar. Is it clear?
Yes, sir.
So as you can see, the water level is here. Okay, the water level will be by the pyramid surface. Basically, it will be here, the water level. If you just increase it to this, and the water level will be here, and the water level will be here. Okay,
Okay, sir.
and this is your, basically this is your ground surface. This is the ground surface. Okay, this is the ground surface.
Okay, sir.
Now here is a problem. It's telling that a confined aquifer, talking about a confined aquifer, is 6 meter deep. That means this is 6 meter, and the coefficient of permeability in the soil is 2 meter cube per day per meter square. That means the value of K is given. The wells are 100 meter apart. The wells are 100 meter apart. That means you have two wells basically, this well and this well, and they are 100 meter apart. Both are in the confined aquifer. This is 100. Okay. The difference in the water level elevation in the wells is 3 meter. That means the difference, this is the difference, all right? Delta H. Draw this. I think that would be better. Maybe if you don't have the figure, then I can draw it, no problem. So the ground surface, this is the impervious layer, this is another impervious layer. Okay, so this is the rock, solid rock, solid rock, and this is your T well here, and this is a T well here. So as you can see, the water level is here, and the water level is here. So the difference in the water level, basically, delta H. They are 100 meter apart. Two wells are 100 meter apart. Delta H is given. Delta H is what? Uh, Difference in the water elevation in the wells is 3 meter. So delta H equals to 3 meter. Find the flow rate and the superficial velocity through the aquifer. So flow rate equals to what? We know the equation for the flow rate. The equation is this: Q equals to, first of all, equals to K into A into delta H by delta L. What is K, by the way? K is 2 meter cube per day per meter square. So 2. What is cross sectional area? What is cross sectional area? Now you have to understand one thing. The water is flowing from this to this direction. Okay. So which cross sectional area we are taking? You are taking this cross sectional area. Is it clear?
Yes, sir.
Yes, sir.
Okay. So it's like this figure. One tube well, second tube well, and cross sectional water is flowing from there to there. This is you're taking this cross sectional area. Now the thing is, now the thing is, um, here this is ground, right? This is ground soil. So we know the depth. What is the depth, guys? The depth is 3 meter. Am I right? No, 6 meter. The depth is 6 meter. That's okay. Now to take the area, you have to take also the width. Am I right? In this direction. Am I right?
Yes, sir.
Yes, sir.
Then you'll get the area maybe. Now the question is, um, how far you will go because this is soil. You may extend from there to there, right? How far would you go? Now the thing is, you have to go maybe. That's why you have to take it for per unit width. You have to take per unit width. That means we will take for 1 meter. We'll take for 1 meter. Clear? Per unit width.
Yes.
Okay.
Yes, sir.
1 meter wide. Okay. The fluid for section is. And what is delta L?
Cross section area. Sorry. It's a distance.
Okay. So 2 into 6 into whatever it is, 0.03. So 0.35, right? This is 0.35. Now all here were in SI unit. This was in SI, and this is unitless because meter cancels out. So basically it will be meter cube per. কেটা কিসে ছিল কেটা বলো তো মিটার কিউব পার ডে রিমেম্বার মিটার কিউব পার ডে পার মিটার স্কয়ার সো এটা হবে মিটার কিউব পার ডে সেকেন্ড লিখে দিও না so superficial velocity easy you know the q, you know the area is what 6 into 1, so superficial velocity is v equals to q by area, so 0.35 divided by 6 whatever it is, 0.35 or 0.36, let's say 0.35 whatever it is, divided by 6. Clear?
Yes, sir.
Okay. If a well is sunk into an unconfined aquifer and the water is pumped out, the water in the aquifer will begin to flow toward the well. As the water approaches the well, the area through which it flows gets progressively smaller. Therefore, a higher superficial velocity is required. The higher velocity, of course, results in increase in loss of energy and pressure gradients must decrease, forming a cone of depression. What's happening here? So far we have discussed unconfined. Let's talk about confined aquifer. Let's talk about confined aquifer. Ground surface, there is no um, solid rock, so this is the direct water layer. Okay, and this is maybe a confined layer at the bottom. Now, if you inject, if you inject um, tube well here. Okay. If you inject a tube well here, what's happening? Look, um, in this tube well, what we do is we have a screen here. We have screen here. Screen means filter, like right? Screen, so that screen ছাঁকনি আঁকে, okay? So that only water can pass. The soil particle cannot pass. Is it clear? So
Yes, sir.
we have
Ye-
gravel particle actually surrounding here. And usually you have higher, larger particles here, natural particles, okay? And we design this well in such a way so that we have gradually smaller particles here. First you have larger particle, and as you go towards the well you have smaller particles, larger particle, but as you go towards the well in this direction you'll have smaller particles. We design the well in such a way. Is it clear?
Yes.
Okay.
Yes, sir.
Okay. Now, why? Because we do not want the soil particle to enter into this um, screen, through this screen. Okay.
স্যার পার্টিকেল বড় থাকবে না ছোট থাকবে স্যার এটা কিভাবে বুঝবো? কারণ স্যার এটা তো না দেখে বোঝা যাবে না।
Exactly. So we design this. We basically surrounding this well. These are the natural particles. These are the natural particles. But surrounding these wells, we design this particle and we make a hole and replace the natural particles with this designed man-made gravel, and we will see how to design it. This is called gravel packed material. Is it clear?
ইয়েস স্যার।
We design it in the lab. I mean, we design it and we create this in the lab, and we replace it. Not in the lab, you can also design it in the field if you have the design and the appropriate particles. So, yeah, like this. Okay, clear? So you can see
Yes,
that
sir.
gradually um, these particles gradually are having from larger pore or larger opening to smaller openings, Now the thing is, if you go to the smaller openings, what happens? The velocity increases, right? Cross sectional area if decrease, the velocity increases. Am I right?
Yes, sir.
Right. Now, if the velocity increases, then the head loss also. I mean, the frictional loss also increases, right?
Yes, sir.
Now, if there is frictional loss, so what happens? This water layer that actually goes down. Okay, higher velocity increases loss of energy and pressure gradient must decrease, forming a cone of depression. That মানে কি মানে হচ্ছে velocity বাড়লে pressure head কমে যায় না? If the
Yes, sir.
velocity is
ইয়েস
decreased, then
স্যার।
the pressure head, if the velocity increases, then the pressure head decreases.
Decreases.
Therefore, you'll see that since near the well the velocity is high, so near the well the pressure head will also be low. Will be low. So water level will go down. Pressure head কম মানে কি? Water level will go down. বুঝা যায়? বুঝা যাচ্ছে?
Yes, sir.
Yes, sir.
Water level will go down. এটা হচ্ছে water level. Current water level. So when you are pumping the water is going towards the well, velocity is increasing, pressure head is decreasing. Therefore, the water level is decreasing. Therefore, you will see that a cone of depression, and it happens all around the well. So it's like it forms a cone of depression. Depression মানে কি নেমে গেছে, right? So cone of depression, original water level, but while you are pumping, the water level goes down. This is the actual water level during the pumping. Is it clear? Is it clear?
Yes, sir.
Okay, this is called forming a cone of depression. So I'll take a break here for 1 minute and then I'll for 2 minutes and I'll come back again, inshallah. Okay, guys. So, you have any questions on this?
No, sir.
No, sir.
No, sir.
So, the reduction in the water level is termed as drawdown. And what is the drawdown depth? The drawdown depth is this depth. Okay. The rate of water flowing towards the well. That means the rate of water flowing towards the well. The rate of water flowing towards the well is equal to the rate of water being pumped out of the well, is equal to the water being pumped out of the well. The condition is at equilibrium and the drawdown remains constant. Okay. Now, if, however, the rate of pumping is increased, the radial flow toward the well must compensate and therefore results in a deeper cone or drawdown. So, in that case, if this rate of extraction is higher than the flow of water towards the well, then what happens that this water level will further go down. Okay.
Yes, sir.
Okay. Now, hydraulic characteristics. We need some equation through which we can determine the flow of water through the aquifer. So first look at the unconfined aquifer. So this is an unconfined aquifer. What's happening here is that this is the ground surface. This is the ground surface. Okay. And you have a well here. This is a one well. Okay. This is a well. Test well. This is the test well. Okay. Now you have two more. By the way, from this well, you are extracting the water. You are extracting the water through this well. Okay. Now you have two other wells. One is here. Another one is here. So you have two other wells. Now these two wells are just observation well. They are not extracting the water. They are not extracting the water. They are like just piezometer. Clear? They are not extracting the water. Only this test well is extracting the water. These two wells, this and these, are just observation well. They are, that means they are being used to observe the water level. They are not directly extracting the water. Now, since you are extracting the water from this well, therefore there will be a drawdown. Initially, the water level which was here now will go down here. Am I right?
Yes, sir.
Okay. Now you can observe the current water level due to this drawdown through this observation well 1 and observation well 2. Let's name it 1 and 2. This is 1 and this is 2. Okay. From the center of the test well, any distance, we call it x, and this is the impervious stratum, this is y. Okay. So any point at this water level, any point, for example this point, the horizontal distance from the radius from the center of the test well is x, and the vertical distance from the stratum, impervious stratum, is the y. Similarly, from the impervious stratum, the water level in this observation well 1 is H1 and observation well 2 is H2. Remember that this H1 and H2 is from the bottom, that means from the impervious stratum. Similarly, from the center of the test well, the horizontal distance of the center of the test well observation well 1 is R1, and for observation well 2 this is R2. Center to center distance from the test well. Clear?
Sir,
Yes.
why the x distance is taken at the middle?
This is any point. This is for any point. Variable. This point can be here, this point can be here, here, anywhere. So it's a variable.
Okay, sir.
Now, discharge through this test well is K into A into delta H by delta L. Now, what is area? Let's look at the area. Area is basically the area. I mean, if we zoom this here, you'll see that the water is entering through this well screen all around. Am I right? All around.
Yes, sir.
That means your cross-sectional area will be this area. Am I right?
Yes, sir.
And
Yes,
what is
sir.
this area now? This is area is basically twice by RH, twice by RH, right? Sorry, twice by R. This is twice by R. This is what? Twice by R, am I right?
Yes, sir. Perimeter.
Into H, right? Twice by R into H, right?
Yes, sir.
Yes, sir.
So um, we can write area as twice by, if we replace R as X and H as Y, so twice by Y into X, twice by X into Y. This is the area, cross-sectional area, twice by X into Y. Clear?
স্যার বুঝি নাই স্যার আর
Um, is it clear? Twice by RH, is it clear?
স্যার
So R is what? R is basically the horizontal distance, right? Right?
জি স্যার
Now let's call this X, right? If this is the drawdown up to this level, then your area will be this, am I right?
ইয়েস স্যার
An area. Now at this point, or at this point actually, what is your radius by the way? Your radius is X. If I call it X, am I right?
ইয়েস স্যার
And what is your height here by the way? Height will be Y.
ওয়াই
So we are replacing R and H as X and Y. So twice by XY.
ওকে
Into
স্যার
F into delta H by delta L. So delta H by delta L, we are replacing it with dy by dx. Same thing, delta H by delta L, dy by dx. Okay. Slope, basically this is the slope, hydraulic slope, hydraulic gradient, I would rather say. Twice by hxy is the area at section, and flow velocity, kf, velocity equals to what? K into delta H by delta L. So you can write delta x by delta, sorry, delta H is delta Y, sorry, delta Y by delta X. Okay. Hmm? Clear?
ইয়েস স্যার
Yes, sir.
Now, integrating over the limits, what would happen? আমাদের লিমিটটা কি এখানে? ধরো আমি যে লিমিট যদি বলি, ফর এক্সাম্পল, যে R1 to R2, R1 to R2, হলে তোমার at R1, what is the y h1? At R2, what is the y h2? So therefore, if you put R1 to R2, you have to put H1 to H2, right? So Q, you can rearrange this 1 by x dx twice pi y dy and pi k. These are the constant. So I can directly write this by rearranging. And if you integrate this, 1 by summation of 1 by x dx is what? Ln x, right? Huh? Ln
Yes,
x.
sir.
Ln x. Q is the constant here. So R2 here is the R1. So you can write Q ln R2 minus ln R1. That means you can write ln R2 divided by R1. Right? Am I right?
Yes, sir.
Sir.
Similarly, and this in the right hand side, this is y square by 2. And instead of y square, this is a limit. So h2 square minus h1 square by 2. Okay? Is it clear for everyone?
Yes, sir.
Yes, sir.
So by rearranging, finally you get this. Q equals to pi kf h2 square minus h1 square divided by ln r2 by r1. Now this is very important to understand which one is 2 and which one is 1. Which one is 2 and which one is 1. Which one is you can see that r2 is at the top numerator and r1 is the bottom at the denominator. So you have to understand it very carefully. You have to check it very carefully which one is what. R2 is the farthest one. R1 is the nearest one. R2 is the number 2 is the farthest one. 1 is the nearest one. Is it clear?
Yes, sir.
Yes.
So the farthest one, R2 is the higher. The R2 will go at the top, and the smaller one will go at the bottom denominator. Clear?
Yes, sir.
And
Yes.
h2 square minus similarly h2 square minus h1 square. This is the equation. Q equals to pi kf h2 square minus h1 square ln of r2 by r1. Okay. Well, now if we solve a problem here on this, you know what they're telling. A well is 0.2 meter inch diameter. So you have a well here, extraction well. It has a diameter of d equals to what? 0.2 meter. Okay, extraction well, and pumps from an unconfined aquifer. This is the unconfined aquifer, which is 30-meter deep. 30-meter deep, unconfined aquifer. Now, due to the extraction, there will be drawdown. So the water level from here will go down to there. Now the water level is here. Okay, this is how the drawdown has taken place. Cone of depression like this. Okay. Okay.
Yes, sir.
Yes, sir.
30-meter deep at an equilibrium. Rate of 1,000 meter cube per day. So this is at equilibrium. Okay. Rate of 1,000 meter cube per day. What is the Q here? The Q is here. This equal Q is 1,000 meter cube per day. Two observation wells are located at distances 50 and 100 meter. The observation well 1, the two are observation well 2. So this is basically 50-meter distance and the second one is 100-meter distance. Okay, so we can call them basically R1 and R2. They have been drawn down. Look, they have been drawn down by zero point 0.3 and zero point 0.2 meter respectively. তার মানে বেসিক্যালি ইনিশিয়াল লেভেলে কোথায় ছিল ওয়াটার লেভেল? এটা হরিজন্টাল, এই যেটা, okay, which was initially 30 meter. Anyway, so this is 0.3 meter, এটা হচ্ছে 0.3 drawdown. তারা কি বলছে? They're talking about drawdown. This drawdown 0.3 meter. This is the drawdown 0.3, 0.3. And at this well number 1 and well number 2, the drawdown is 0.2 meter. 0.2 meter. এটাই বেসিক্যালি বলতে হবে। Okay, is it clear?
Yes, sir.
Okay. What is the coefficient of permeability? That means K, estimated drawdown at the well. So basically this is easy. You have the equation. What is the equation you have? You have Q equals to K into, remember, pi into K, pi into K into H2 square minus H1 square, H1 square divided by ln of R2 divided by R1. And what is your Q, by the guys? What is your Q? They're asking you to find coefficient of permeability. That means this one, right? Right?
Yes, sir.
Q. What is Q, by the way? Q is 1000 meter cube per day. So Q equals to 1000 meter cube per day. By what is H1 and what is H2? What is H1 first of all? H1. Remember, again, remember, H1 and H2 is from the bottom. H1 and H2 is from the bottom, not from here. Okay, so therefore, here you have been given what? You have been given the drawdown. This is 0.3 meter, am I right? 0.3 meter. 0.3 meter. So therefore, you have to determine what? You have to determine H1 from the bottom, am I right?
Yes, sir.
So H1 will be what? H1 will be 30
30 minus 0.3.
minus 0.3. So 30 minus 0.3. This is H1. Similarly, H2 is from the bottom, and that is what? That is 30 minus, oh, I'm sorry, I'm doing the wrong thing. Not from there. Here, H2 is here, right? So H2 is equals to 30 minus 0.2. This 30, this the whole one is 30 minus 0.2. So then you'll get this. Okay? Clear?
Yes, sir.
H1 equals to 30 minus 0.3. These are in meter, right? Meter. And H2 equals to 30 minus 0.2 meter. What is R2 and R1? R1 is 50, R2 is 100. R1 equals to 50 meter and R2 equals to 100. So put the values here. Q equals to 1000. Pi is here. K is here. H2 is what? 29.7 square minus H2 is what? 29.8 square ln of 100 divided by 50. Am I right?
The 29.8 square minus 29.7 square হবে না?
I'm sorry. Yeah, you're right. So H2 minus H1, right? So 29.8 square minus 29.7 square. Although it will bring you the same thing, but it's okay. So calculate the value, please.
37.081.
37.08. So you can write K equals to 37.01. The question is, what will be the unit? The unit will be meter cube per
Day.
day. Why? Because Q was in per day. Remember, okay? So it will be, or you
স্যার
can
আমি
directly write meter per day. That's it. Meter per day. Meter cube per meter square day or meter per day, whatever you like. Clear? Clear?
ইয়েস স্যার
Yes, sir.
Yes, sir.
Now, that's the one. What is the coefficient of permeability? Second question is estimate the drawdown at the well. That means now we have to estimate the drawdown at the well. That means this portion, this drawdown. You have to estimate this drawdown. How? Remember, now you already know. Now you already know the value of K. You already know the value of K. So that's why we can easily calculate the drawdown from there. You have to use the equation again. Q equals to pi k h2 square minus h1 square divided by ln of r2 divided by r1. Now, which drawdown you need to know? You need to know this drawdown. This drawdown, am I right? This one.
Yes, sir.
So you have to include this well here. So therefore, in this part, we will make this 1 and we will make this 2. If we include this well, then you will get from the equation, you will get h1. Am I right? H.
Yes, sir.
If
Yes,
you
sir.
get h, then you can easily calculate delta h because h equals to 30 minus delta h. Is it clear?
Yes, sir.
For this, you can calculate this. So from the equation, we will calculate this. And we have made this h1 here. So Q, you already know what is Q. Q is 1000 meter cube per day. Okay. Acha. Then what is K? K we have already determined 37.01 meter per day. Then what else, guys? H1. You have to determine this H1. What is H2? Tell me. H2. Now the thing is, this H2 is and this H2 is not similar, right? Which two wells we are considering now? We are considering this one and this one. So this is our one and this is our two now. Previously this was one and this one was two, but now this is one and this is two. Is it clear?
Yes, sir.
So therefore your H1 is this one now and H2 is this one. And H2 is what? H2 was previously H1, 30 minus point 0.3, right? 30 minus point 0.3, right?
Yes, sir.
Right. So 30 minus point 0.3. This is 29.7 meter. What else, guys? R2 and R1. What is R2? R2 is for this well, this well, this well. What is the R2 here, guys? R2 is given, right?
50.
Now, this R2 and this R2 is not similar. Now, yeah, this is not 2, so this is 50. Okay? This is 50. Now the question is, what is R1? R1 is the, remember, R1 is the closest one. Now what is the closest one? The closest one was this one, right? 1.
Yes,
So
sir.
R1 will be for this well. From the center of this well, from the center of this well, center distance of this. Now what is this? This is R1 now. Now this is basically radius of this well. Am I right?
Yes, sir.
Yes, sir.
What is the radius of this well? Diameter is 0.2. So radius will be what?
Point one.
D by 2. D is 0.2. So 0.2 by 2. We can write it here. R1 equals to diameter by 2, which is 0.2, right? Yeah, 0.2 by 2 is 0.1 meter. So you know everything. You know 1000 by K is 37.01, H2 is 29.7, H1 we don't know. We have to calculate this. Ln of R2 is what? 50 divided by zero point 0.1. So if you calculate this, you'll get the value as, can you please calculate it? So basically this is the equation. You will get H1 as 28.8 meter. From here you will get H1 equals to 28.8 meter. So therefore you will have the drawdown delta H as what? We can
30
always
minus 28.8.
write that RT equals to H1 plus delta H. Delta H plus H1 is 30. So now delta H plus H1 equals to 30. So delta H plus H1 is 28.8 equals to 30. So you can calculate delta H equals to 1.2 meter. Delta H equals to 1.2 meter. Drawdown at the well. This is the drawdown at the well. Clear?
Yes, sir.
So that's the end of the problem and the lecture. Any questions, guys?
No, sir.
Okay. Thank you very much. Have a good one and stay safe.